Hello everyone, we can start. This is, well, first of all, welcome you all to this webinar, which is going to give a very short introduction to Blender, BlenderFDS, and to the cloudHPC we provide. I hope you can hear me all right. We can start step by step. So this is Ruggero Poletto from the Italian company CFD Service. We are here to go through a brief demonstration of BlenderFDS, how you can import the geometry, how you can set up your FDS case, and how you can actually run a simulation using cloudHPC. If you can hear me all right, just let me know, because during the whole webinar you can interact with me and you can interact with making questions. You can ask for clarifications at any time using the chat. The chat is available on the right hand side of the YouTube video, so feel free to type everything. I'll keep an eye during to the chat during the whole presentation, so feel free. It's a good opportunity for you to get some replies. Before we actually start, a brief presentation of the company. CFD Services is an Italian startup. We got founded in 2018, so this is our 5th year. We have 3 main business areas. The first one is software development, in particular in engineering applications. Then there is the cloudHPC we're going to go through, and eventually there's the consulting services in engineering, in mechanical and civil engineering designs. Today, as we said, we're going to talk about BlenderFDS. Many of you might have heard of that. Might be dealing with FDS and might have heard BlenderFDS as a GUI to set up the FDS input file. Well, yes, it is. It is a GUI. It is actually a plugin for Blender. So in order to use BlenderFDS, someone needs first to install Blender on his own computer and then add BlenderFDS as an external plugin to that. BlenderFDS is developed by the Italian Vigile del Fuoco Emanuele Gissi, together with our community, let's say, of developers. So it's a completely open source code. Yeah, I mean, it has some basic functionalities in order to set up a case with FDS. You can obviously take advantage of Blender functionalities, first of all, because Blender is a sort of 3D modelers. It allows to create a geometry, to set up let's say visualization for the geometry, and so you can take advantage of Blender. There are several also import files for Blender, and using BlenderFDS is a specific tool that helps you defining the FDS input file for Blender. As we said before, BlenderFDS is a plugin that can be used inside of Blender. Okay, so the first thing to install BlenderFDS on your computer is just to install Blender. So just follow this link and install, let's say, the most recent version of Blender. Once you have done that, you can go to the BlenderFDS website, actually the GitHub repository, and download the latest version of BlenderFDS. It's a zip file, and following the procedure specified here, so go to Edit in Blender, Preferences, navigate to Add-ons, specify Install, and select the zip file you downloaded from this second URL. Well, in this way, you can install the BlenderFDS plugin inside of Blender. Once you follow this procedure, you need to go again to Add-ons and activate, so just tick Import Export BlenderFDS and load BlenderFDS default settings. This is a procedure, let's say, that needs to be done the first time you want to activate BlenderFDS on your Blender installation. In order to verify if BlenderFDS has been installed, well, on the right hand side of Blender, you can see the FDS case config with the FDS time, MISC, React, and so on and so forth. So FDS commands which are available to users in order to set up the FDS simulation. So once you see that, it means that you completely and positively prepared Blender and BlenderFDS to be used by for your FDS simulations. So let's start with our small example. We're not going to go through all the functionalities of BlenderFDS because this is not a tutorial, it's just a very short webinar, but still we can see something. So let's start from the basics. I prepared a car park geometry, a very simple one. Inside of the car park, which is highlighted here, is transparent. I placed the fire scenario, which is this red part over here. It's supposed to be a car inside of the car park, and obviously inside of the car park I had to prepare the grid. So a vent, a ventilation, a window, sorry, a ventilation surface from which air can get inside of the domain or go outside of the domain, depending of what we need to do. Sorry, I'm going out of Skype. So I prepared the grid. There are two supply surfaces. Not sure you can see that. I just zoom in. One is this one. There is a pipe, a duct from out at the end of it. There must be a fan or something, which is kind of pushing the air inside of the domain. And then there is another supply surfaces. This surface over here. So another point in which we are injecting air, fresh air coming from outside inside of the domain. And obviously there must be one exhaust, okay? So if we want, it's this surface over here, it's an exhaust fan. So a fan which absorb air coming from the domain and going inside of the exhaust and then out of the domain. So we have two supplies, one exhaust, and one, let's say, open boundary, like open boundary of the domain, from which the air can go inside or outside, depending on the balances between the flows between the two supplies and the exhaust. Obviously, this is kind of is there to equilibrate, let's say, the differences between inlet and out, supplies and exhaust fans. Obviously, the whole system is meant to work in a way that this car is burning, so it's producing smoke, it's producing CO, in particular, it's producing heat. And we supply fresh air through the two supply points, we saw that, and step by step we want to extract in particular smoke and the heat produced by the combustion of the car. In here, in order to create this drawing, I used Salome. It's another open source software. You can use any 3D modeler as you want. I know that as a commercial software there are a number of that. Now it's quite popular, Revit, in particular for civil engineering applications, but that is one. There are several others such as CATIA, Google SketchUp. I don't want to just to forget any, Solid Edge, SolidWorks, Inventor. There are so many 3D modelers. You can use any of them as long as you are able to generate, so to export from them an STL file. This is the default file format that can be read by Blender as a geometry. Someone can extend the Blender functionalities in order to read some more file formats, but it needs to install others plugins. So at least according to me, it's easier to export STL and then import the STL into Blender. So in here, I already prepared this. So I'm just showing you that. 1 second, I'm just going to my desktop. I just prepared inside of here. Inside this folder, I just prepared the input STL file of the geometry. There is obviously the car park exhaust, fire, grid, and supply. So everything we read. So the whole geometry of the car park, and then each single item, let's say, we want to define within our car park geometry. So, well, it's now time to go to BlenderFDS. So let's open Blender. In here, this is Blender, the default user interface of Blender. As you can see here on the right hand side, I already can recognize the FDS properties. This allows me to understand that I installed correctly the plugin of Blender. So I've done a good work in the installation part. So my let's say environment is completely empty. So first of all, I start importing the STL file. So I just go to the directory where I define the geometries, and using Shift and the mouse buttons, I can move and let's say get closer to the geometry in order to interact with it. Well, first of all, I cannot see actually what's inside of that. So by pressing here, there is it's called X-ray button. I can actually let's say monitor in a better way what's inside of my geometry. All right, and in here I can obviously see the features of my geometry. I can see the fire, I highlight it. On the right hand side here, there is a menu with basically all the input I read that Blender read from the STL file. So there is a fire, there is the grid, so a window opening towards the outside. There are the two supply fans, and I'm pretty sure there is also an exhaust fan as well. So this is the first step. The first step is just to load the geometry, and then second step, we need to convert this geometry into the correct input for FDS. I don't know how many of you are aware of that, but FDS transform the geometry from whatever shape we have defined into a sort of pixelated geometry. So we had somehow to define pixels in our geometry. So I just select the car park, which is the biggest geometry I have. Automatically, I am redirected to the object properties. If not, I just have to click this property over here. Well, and in here, I have the properties of my car park. Yes, I want to convert the car park into an obstacle. So this pixelated geometry from FDS. And by doing so, BlenderFDS gives me a certain level of options. So I can use the bounding box of the car park geometry. Bounding box means the minimum and maximum X value, Y value, and Z value. So I just create a rectangle that actually involves all the car park geometry. So by selecting XB, I activated that and just leave bounding box, and then I press show FDS geometry. As you see now, I can see the rectangle which is being defined in FDS, and I can actually click here and show FDS code to see the obstacle as actually converted from my STL file into the obstacle in BlenderFDS. So I can see the car park, and this is the bounding box as defined in FDS. So there is X minimum, X maximum, Y minimum, Y maximum, Z minimum, and Z maximum. Okay. So I just hide it. Well, probably bounding box is not a good choice because we just use one single rectangle in order to reproduce the whole of the car park. So it's better to use what we call voxels. So in this way, we try to, let's say, discretize this geometry into several small rectangles, each of which is going to be represented by one single obstacle. So let's start creating this. This is called voxel in BlenderFDS. Let's start creating these voxels with the dimensions of 1 meter. All right. So as usual, I just suggest always to press this show geometry. And in here, I'm not sure you can see, there are all the rectangles that have been generated by these voxelization properties. there are these 3 rectangles and several others scattered all over the geometry. Obviously, the accuracy which we are using in order to reproduce the geometry depends on the voxel size, so on the dimensions of the pixel we are using to replicate the car park geometry. And here I can see the FDS code, so show FDS code can actually show me the whole FDS code, and this time I don't have just one obstacle as I used to have before, but I have several of them, so many of them, each of which is kind of reproducing a small part of the whole car park geometry. Probably using a 1 meter resolution is not good enough. Actually, I can turn that to be 0.5 meters. So let's go back and show FDS job property. You see 0.5 meter, the situation is definitely much better, okay? And we are able to be more accurate in defining the geometry. And obviously, again, I can see my geometry as defined in here as input file. Well, in theory, we could carry on this reduction of the dimensions as much as we want, okay? So 0.25 meters, we activate that. The real point is that the smaller are these voxels, the more time it takes to BlenderFDS to convert this geometry into the pixels. Now with 0.25, you see, it is taking few seconds. You see the accuracy is great, it's lovely, but it took us, I don't know, 15 seconds. So just pay attention when modifying this number. Pay attention because it may take really a long time in order to actually generate the pixelization of the whole geometry. And in particular, if you want to see that, like show and hide FDS geometry, it can take really a long time. So we hide the geometry, we inspect the FDS code once again to be sure that everything is correct. And then this is done. The setup of the geometry can be considered correctly. So 1 second, I'm hiding the geometry. You see the voxels, which are now quite small, 0.25 meters. It takes some time to Blender and to BlenderFDS to handle with this geometry type. Yeah. So this is the code lines which is generated to define the geometry, and that's it. So with the car park, we are happy now in this moment with the current configuration. We are going to move now to the exhaust. Exhaust is, exhaust is this small geometry, okay, from which the air goes out of the domain, okay? So we are extracting air from the domain and moving and taking it anywhere else. Well, in this case, we cannot use obstacle, okay, because this exhaust is a surface. It's a surface that lies on the geometry of the car park. So we'd rather use a vent. Vent is a ventilation surface. This is how I prefer to call it. And it's a surface in which we can apply a specific boundary condition. Because in general, all over the surface generating the car park, they are defined as inert, so as wall surfaces. On the exhaust, we can apply a different surface. In this case, a velocity, an air extraction from the car park. So yeah. Again, we define that as bounding box. Remember, we need to define how we want to define this geometry. At any time, we can click on Show FDS code and actually have a look at the FDS code. What is nice about having this bounding box for a vent is the fact that we take with just one line the whole vent, and for one vent, always make sure that one among X, Y, and Z coordinates, they have the minimum and maximum exactly the very same number, so 1.4 meters in this case. So yeah, the vent is defined correctly. Now we want to apply a surface. Okay, it's to say, listen, in this vent, there is a specific boundary condition, and this boundary condition is air going out of the domain. So yeah, so I activate the surf ID and then I want to select one of them. The default surf ID, they are not, let's say, good, at least for this example we have over here. Okay, so we want to generate a new surface. So we go here to the material properties and we generate a new surface. We call it outlet 1. All right, and under parameter we can specify the velocity outlet surface. Okay, if I remember correctly, velocity outlet is, we specify velocity 2 meters per second. Positive value means flow going out of the domain. Negative value means flow going inside of the domain. Okay, so I use this outlet 1, I define this outlet 1 surface with velocity equals to 2, and now we go back to the surface and automatically that has been applied to the outlet. Okay, I hope this passage is clear because we have to do it 2 or 3 times now, in particular when defining fire and so on and so forth. So I skip for 1 second the fire. I move to the supply, which are somehow similar to the exhaust. A supply, let's say, is a boundary condition of the air going inside of the domain, while in the exhaust the air is going outside of the domain. So we already know that the main difference is in here, in which we define a velocity as a negative value. Okay, but this time the supply is divided into 2 parts. Okay, so again we turn this to be a vent. Okay, under XB, since we have 2 different supplies, we don't use bounding boxes as we did before, but we use faces. If we show FDS, if you turn that to if you show the FDS code, we can see we have now 4 faces, okay, because there are 4 triangles, but each of these faces has there are 2 levels, so 1.9 meters height, one of the 2 supply fans, and 2.1 meters high, the second one. Okay, again we activate surface ID, and this time in here we define the inlet one. Again, it's a velocity vel equals minus 2 meters per second. Okay, this is a velocity in meters per second. Obviously the flow getting into the domain depends also on the area of the supply. So the flow going out of the domain from the exhaust fan is, again, we have the same velocity, which is 2 meters per second, but the total flow depends on the supply area, okay, on the exhaust area. As well, this is happening for the supply. So there is an imbalance of the flow getting inside of the domain and the flow going outside of the domain. So for this, we have to define also a grid. Okay, this is another vent, okay, in which we define an open boundary. Okay, so this means that this, I need to activate that as well, yeah. This means that through this vent is an open boundary, and it allows this vent to balance the misflow between the supply and the exhaust fan. Misflow that will always exist. Also in real life, this is happening. Usually we don't have exhaust fans and supply fan providing exactly the same flow rates. The flow rates are slightly different, and they are balanced by openings, ramps, grids, or other windows which are open to the outlets, to the atmosphere inside of the domain. Let's go to the fire transformation, to the fire part. Well, this is very good. This is, let's say, the core of our geometry setup. Okay, again, this is an obstacle. We define this obstacle as bounding box. Very good, as we did before. This time, again, we have to define a new surface. Okay, we call it the fire surface. All right, and as a parameter, we define HRR per unit of area, which is the heat release rate per unit of area, equals to whatever we want, whatever actually we want. We need to calculate that from the regulations, the fire regulation that we are applying. So in here, I just apply 10,000. Okay, the units of this is kilowatts per square meters. Okay, so we're just applying quite a huge HRR per unit of area. But we're gonna see later how we can distribute that. Okay, so in here we define the surf, and we go back here and we have already applied the fire surf ID. Okay, so we have this obstacle is calling the fire surf ID. Okay, well, let's say at least from what I suggest to do, everything is now done. Okay, and we can export the FDS file from Blender. So going from file, export FDS. Oh yeah, it always asks to save the Blender case. So we just save that. We just save it with today's date, which is the 17th of January. Okay, we save it, and then file, export FDS, and we call it scene 2. Export the FDS. So now if I go here, I can actually see, maybe I had to refresh. Maybe it didn't work. Let me try again. Export scene 2. Yeah. So let me just check again. I can't find it. Maybe I was incorrect. Let me try again. Sorry, I cannot find the file. I just export it to the desktop. Okay, so this is, let's say, the default geometry as defined by BlenderFDS. Oh, I forgot one thing. In this geometry, automatically we have time. We had the 3 surfaces we defined before. We had the geometry, the obstacles, as defined, let's say, again in BlenderFDS, and eventually here we have all the 4 vents we defined. We forgot something which is quite fundamental actually to run the simulation, which is the mesh. Okay, usually to do that I just duplicate the car park by pressing Ctrl+C and Ctrl+P. So I just duplicate the whole geometry, and this time as name list I just set mesh. All right. So by doing so, automatically we are asked how many cells we want to set in X, Y, and Z direction. So we just set 100, 100, and then 30. Okay, and by automatically it takes the bounding box of our geometry. So yeah, I just rerun the export. So file, export FDS, and I just go into my desktop. Export FDS. Yeah, sorry, I forgot that before. So open it. Yeah, compared to what we had before, now we have this line, which is the mesh. Mesh is actually the computational domain in which the simulation is performed. Currently, just leave it one mesh as it is right now. So yeah, this is, let's say, the base FDS file that can be used in order to add advanced functionalities inside of Blender. Okay, let's go back to the presentation and let's see what I suggest to do now. There are, let's say, few things which by default BlenderFDS doesn't do, or let's say it can do, let's say, in a manual way, and at least as far as I suggest is to work directly on the FDS file exported by BlenderFDS. So the first one in the regulations for fire preventions, usually you don't have to apply a constant HRR curve, but this curve is a variable in time. To do that, there is a command to add to the surf we just generated, which is ramp q, fire ramp, and then we create a sort of table, which is the fire ramp table, inside of which we define a t parameter, which is time, and an f parameter, which is a multiplier. Okay, so this means that at time 0 we are multiplying this HRR per unit of area by this factor 0.17 and so on and so forth. At time 5.3 the factor becomes 0.38. At times 15 it becomes 1, and then it decreases as the time is carried on. In this way, okay, it is possible to modulate the heat release rate in time, okay, and this is very good, in particular when applying the fire safety regulations. So we can keep, let's say, a separate table in which we just copy and paste this ramp, and we just modify slightly the times as we can see here. Then there are slices. In most of the simulations we want to perform, it's mandatory to have a control of the smoke visibility and the temperature and the carbon monoxide concentration and several other parameters, but at certain levels. Okay, so we can create a slice of the domain, okay, which is this one we can see in this image. And how we do that? Well, we added this command to our FDS file. We added the end slice command pbx10. It means this slice is aligned, is normal to the x-axis, and it occurs. It is generated where x equals to 10 meters. And we are monitoring, what are we monitoring? Well, quantity, temperature. We are monitoring temperature in this slice at 10 meters. In this other, we are monitoring velocity. Velocity is a vector, so I suggest always to put vector equals to true in case we want to monitor velocity. And in these two slices, which are aligned with the z-axis, so they are going to be horizontal, we are monitoring mass fractions of carbon monoxide and soot. Okay, so space ID can be used when monitoring mass fraction in order to specify which, let's say, species we want to monitor. Another thing I often add manually to the text FDS file once it is generated is the control. So we have an obstacle which appears or disappears when a certain condition is reached. Okay, it's like a door which opens when the temperature close to the door reaches 100 Celsius degrees. Well, in that case, we need to append to the obstacle definition the device ID and add a device ID as following. The device ID has this, which is the coordinate of the device, the ID of the device, which is the same one we reported in the obstacle, and then there are these quantities which are to define the controls. So in this way, we define this device is monitoring temperature, and when this set point of 100 degrees is reached, we are going to make the obstacle disappear, because in the beginning we have the obstacle, okay, and it means that when the set point is reached, the state turns from true to false. Okay, so the obstacle disappears. Latch is let's say a way to tell FDS is this state change is reversible or not. So once we set this obstacle to disappear, and if the temperature goes below the set point temperature of 100 degrees, are we re-adding the obstacle or not? Well, if latch true, it means that there is just one change. So once the obstacle is gone, regardless the temperature value, the obstacle is gone. If it is false, it means that it goes back and disappear again and again as we keep on passing this set point, this threshold. So as you can see, BlenderFDS is very useful in generating the geometry. At least the way I personally use it is is for that, and then I manually edit with some advanced configuration the FDS file. But once we have generated the FDS file, how can we run a simulation? What can we use? Obviously, you know, FDS uses a lot of hardware resources in our computer, okay? So for these, we provide, let's say, hardware resources on the cloud. So it is possible to execute the FDS on a remote hardware system and just download the results at the end of the simulation, okay? The benefits of doing that is that you can speed up your simulation because the hardware you are using on the cloud is usually dedicated to HPC, so it's very powerful hardware, very powerful CPUs. You can just you're just paying for the time you're using the cloudHPC resources, so you're not there's no a subscription. It's just pay for the amount of hours you use the resources, and that's it. There is a scalability, so it is possible to really take advantage of a high number of hardware resources. It is possible to run several scenarios of simulations at the same time, or it is possible to execute very big simulations, okay? So for every simulation on the cloudHPC, you can use up to 224 virtual CPUs. It is important when using FDS to remember that someone has to adapt a little bit the FDS file in order to use correctly the hardware resources on the cloudHPC. Well, everything regards, let's say, the most crucial part is the mesh generation, okay? So the last bit we saw before. Well, we need to define multiple mesh lines in our FDS file, okay? This is crucial, okay? So one mesh line does not allow us to use in a correct way the hardware resources we are renting from the cloudHPC. Okay, so we need to define multiple mesh lines, and make sure that the number of cells per each mesh line is above, let's say, 15 or 20,000 cells. That is a threshold. If we go under these thresholds, the scalability of FDS tends to be poor. Okay, if we done that, well, what we can do, we can select the number of CPUs we are using on the cloud equals to the number of meshes defined in our geometry times 2, multiplied by 2. Okay, and using that, we can execute the simulation. Let's have an example. So going back to our FDS mesh definition, if we go and show FDS code, we can actually see that BlenderFDS is generated just one single mesh line. As I said before, we had to divide the meshes in order to have a higher number of meshes, and the cell quantity in this mesh line is 300,000 cells, so there are a huge amount of cell quantities. Well, we can use the split functions, we can activate it over here, and define the number of divisions we want to apply along X and Y and Z eventually, possibly axis. Well, we split into four parts along the X and 4 parts along the Y axis. As you can see now, it says mesh quantity is split into 16 parts. The overall cell numbers is 300,000, but per each mesh is 18,000. And from the presentation we saw before, we said we had to make sure there are at least 20,000 cells per each mesh. So yeah, we are in that range. We cannot divide further, but we are happy that we do that. If I now activate a show FDS code, I can see that BlenderFDS is not generating one single mesh. It's generating several meshes. Okay? Several meshes, each of which represents one single mesh that is going to be assigned to one processor. We now go back to the scene properties where there are the general setup of the simulation, and we need to set up two things. The first one is the number of MPI processes. We set 16, exactly the number of meshes we defined over here. So this is 16 because 4 division in X and 4 division in Y, we have this number of 16, total 16 splits. So we need to assign MPI processes equal to 16. And then another thing we didn't do before is the FDS react. So we need to define what is burning, propane, for example. We need to define the CO, soot yield, heat of combustion, and radiative fraction. Well, most of these quantities can be taken either from the physics of the problem or from the regulations, okay? Using the Italian regulation, the CO yield is 0.1 and the soot yield is 0.07. Heat of combustion, I don't know, it depends on what is actually burning. In our case, we just use 10,000 kilojoules per kilograms. And radiative fraction, again, it depends a little bit on the regulation. In Italy, it's 0.35, but it must be some value similar to this in other countries as well. Well, once we have done that, we are ready to save everything and export again the FDS file. So we export scene 2. Yeah, so we go to the desktop and we open this file over here, and there it is. You see, this time I don't have just one line of mesh, we have several ones. We have surfaces defined before. We can edit the total simulation time, which is 3,000 seconds, whatever we want. We've had the reaction defined right now, the geometry and the events over here. I actually, we could execute this file, but in the simulation I prepared of the car park, I just modified it slightly to be more accurate, to have not to have a constant HRR curve, but to have a time variating one. So I just edit in advance the file with all the features required in order to run properly. So this is the file we're going to upload on the cloud. So, well, to execute the simulation on the cloud, we just go to the cloud.cfdfileservice.it. Actually, if you haven't registered, you can go to this website and click and follow the sign up registration procedure in this page. So in order to execute a case, I have to log in. We have to go to the storage and upload the scene file we've just generated. So I just drag and drop it in here and press save. So this is the scene that we want to simulate, and then we go under simulations, we press plus. Well, we divided the mesh into 16, but if you remember in the presentation, I'm just going back to the presentation, we said to use the number of meshes multiplied by 2. So we're not going to use 16, but we use 32 virtual CPUs. Type high CPU, that is okay for most of the cases. We just select scene FDS and the FDS version, which is 6.7.9. We just submit the job and there it is. The system is already starting. So there is a pending status. Usually it won't last that long, less than a minute. So we just refresh the page and we wait a few seconds from this simulation to go from pending to running. Yeah, there it is. So every simulation is performed on a dedicated virtual machine. So it takes 2 or 3 minutes to actually generate the virtual machine, but once we have that, it will be possible not just to run the analysis, but also to monitor the analysis using the remote desktop. So now just together we're gonna wait for let's say the setup of this simulation to be completed, and we just wait for let's say for the simulation to start. As you can notice, everything is in a web browser. So in theory, I could close everything, shut down my computer, and still the simulation is going to be carried on by the system. So I don't need to be logged in or connected to the platform in order to run the simulation. It's just to execute it in the beginning, and then we just have to wait for the system to complete the analysis. Step by step, this is the output window. Step by step, as you can see, the output is moving forward. So now the virtual machine has been defined. Now there are some preliminary operations like transferring the file to the machines and activating the remote desktop on the machine as well. As you can see, I'm not doing anything. Actually, everything is done automatically by the system. So let's just wait a little bit for the simulation to actually start. We are nearly there, so we executed it at 12:14, now it's 12:16, so in 2 minutes, there it is, now the simulation started. If I now refresh the page, okay, I can see here at the bottom, okay, this is the remote desktop of the machine where the simulation is performed. In here, I can see that FDS log is actually running, and I can double click on smoke view, and this is going to automatically open smoke view and make it to me possible to actually see the domain, see what's happening in my geometry. Okay. So there it is. You can see the geometry has been converted into an FDS geometry, and now it takes some time because there are a lot of obstacles, but the simulation is going to be carried on as required by the user. We have full control of, you see, time step is now started. We have full control of the simulation. We can stop at any time by pressing stop. We just want to stop if we are happy of the results we computed, and automatically the system detects there is a stop and will come to an end and produce the output file. These output files are going to be made available in the storage under here. Okay, so you will have, once the simulation has been completed, all the output files generated by FDS. Let's go back to the presentation, and yeah, I just kept an eye on the chat, but I didn't see any question. I hope I've been clear and I've been boring so far. Well, the costs of the cloud, well, all the software we saw here, they are free of charge. Okay, so Blender is completely free. BlenderFDS is free. The only cost is the cloudHPC use. It's a rent. It's a rent use of the platform basically. So every hour there is a fee to be paid if you are running a simulation. If you don't run a simulation, the cost is completely free. So if you run a simulation, depend on the type of instance we use, the cost goes from 0.04 euro cent per virtual CPU hour to 0.12 euro cent per virtual CPU hour. This is just to give you the minimum and the maximum cost we can pay. Okay, so we are talking about euro cents per virtual CPU hours. And there are no other costs, no activation, no network, no data storage, nothing else. Actually, there are some discounts available. In particular, if every month you run a lot of simulations, there is what we call the progressive discount, which can give you up to 30% discount if you use quite a huge amount, a big amount in cloudHPC. What I can say now is, well, thank you. First of all, thank you all for being part of this webinar. I hope I'm sure I haven't replied all the questions, and probably this has not been a complete train about BlenderFDS and cloudHPC, but I suggest you all to download BlenderFDS and try it yourself on your local computer, and also to try the cloudHPC to run FDS simulation. So you can register for free by entering this website, and you can actually have a benefit of 300 free CPU hours to try the platform in the beginning. If you have questions, you can email us for general info. There is info@cfdfairservice.it, or if there are specific requests about cloudHPC, it is possible to email us at info@cloudhpc.cloud. We also can organize, let's say, dedicated trainings in BlenderFDS or FDS in general. So get in touch with us also if you need that sort of activity. With this, it's everything from today's webinar. I hope you had fun having a look, and I hope this was useful to you in order to getting familiar with these instruments and let's say at least starting using new instruments which are quite popular, not just because they are cloud-based, but also because, at least in Italy, regulations are allowing engineers to use this type of instruments in order to demonstrate the fire safety of any place. Having said that, I say thanks to you all again, and keep in touch using our socials on LinkedIn, Facebook, and Twitter in particular, and see you next time. Bye, everyone.